Hi crypto devs, Liarco here. In today's video we're gonna talk about mutation. Yeah, we're gonna take a look at the ERC1155 token that can be used in order to mutate your NFTs. Let's get into it. I created a dedicated repo for this series so we can work on a clean workspace. You will find the link in the description. However, this project has been created for educational purposes only, so don't expect this to be a ready-to-use tool for production. Please remember, you should never copy-paste code from the internet, so don't do it. Before getting into the code, let's talk about the requirements. There are two mutation types, a basic one and the premium one. Owners of the Genesis token must be able to claim one basic mutation token, so one mutation token per Genesis token. 3 basic mutation tokens can be exchanged for one premium token. It must be possible to query the contract for the claim status, so we can show this on a dApp. Now let's take a look at how to implement this with Solidity. In this episode, I'm gonna focus on code which is available up to tag 01-mutation token. If you don't know what I'm talking about, I'm gonna put a link in the description to a video where I explain how repos are structured in this kind of videos. So this is the project folder. We have a hardhat project in here and the contracts folder. First of all, we need a Genesis token. Any ERC721 collection would work fine, so in this case I simply created an empty ERC721A collection that can be minted for free with no limitations. I like my NFTs to start with an ID of 1, but it's not mandatory at all. Interfaces in Solidity are very useful. I will probably publish a dedicated video about them, but for the sake of this tutorial, you can think about them as follows. They describe errors, structs, events, and functions that will be available in the final contract. In this specific code base, it helps me keep some definitions, for instance errors, in a dedicated file, not to clutter the actual contract. The errors defined here are mainly used during checks, so we can use them to revert when, for example, a token has already been used to claim or the sender has insufficient funds, and so on. Events in Solidity are extremely useful whenever you want to intercept specific actions off-chain. In this particular case, we want to be notified each time a mutation token is claimed, so we can use this information on a dApp, for example. Structs are another thing that can be defined in interfaces. Here, I'm defining the claim status struct, which holds information about whether a Genesis token has already been used to claim or not. Please pay attention here, because of course this is not where we're gonna store the status of our contract. Soon, we will understand where this specific struct comes in handy. The last definition is the burn function. Interfaces should tell about which public functions will be available in the final contract. In this case, we are extending the interface for the ERC1155 token, so everything defined by that interface will be inherited as well. Then, the burn function is the only one that will be used by external contracts in this project, so I'm defining just that one to keep things simple. Now we can take a look at the contract file. At the top, I'm importing some dependencies from the OpenZeppelin library, as well as our own interface. And as you can see, this contract is also implementing and extending some of these. Apart from implementing our interface, this contract is also extending ERC1155 for the NFT implementation, Ownable to protect management functions, and Reentrancy Guard to make sure attackers won't take advantage of reentrant calls on sensitive functions. Then we have some constants. Constant values can be very useful because they help reusing the same values multiple times while keeping the opportunity to edit them from a single place in your code. They also have no impact on gas cost, because the compiler will replace all the occurrences during compilation. So, the values are not added to the contract storage at all. I'm using constants for values like the token type IDs, the exchange rate for the premium token, and the URI suffix. These values will never change at runtime. On the other hand, the Genesis token contract is a bit different. It's defined as immutable. Immutable values work pretty much the same as constants, but you have the chance to set their values in the constructor. Once the constructor is run, the value is then replaced in the compiled code, so in terms of gas cost, this only affects contract deployment. Using an immutable value here instead of a constant is really important, because it allows you to have different Genesis contract addresses for different environments. For example, test and production. The mutated contract address is usually unknown at deployment, so it's important to have it as a state variable so we can change it later. The next two variables are simple Boolean flags to enable and disable the claim and exchange features. Then we have a mapping from uint256 to Boolean values. This will hold the claim status for all the Genesis tokens and will be used by the contract as well as external services like the dApp. The constructor is pretty basic. We get the Genesis token address and the URI prefix as parameters. We pass the URI prefix to the ERC1155 constructor and we initialize the immutable value. Things become interesting with the claim function. It takes a single parameter, which is an array of token IDs, and it has the non-reentrant modifier from reentrancy guard. Each function which has that modifier will follow two simple rules. You won't be able to call it recursively during its own execution. And second, you won't be able to call any other non-reentrant function during its execution. Even if I'm using the non-reentrant modifier, the function is still using the checks, effects, and interactions pattern. This is in order to keep a safe and clean flow. So first, I'm checking that the claim feature is enabled. I loop through all the token IDs, and for each of them, I check both ownership and claim status. And then, if everything is fine, I update the claim status and emit the claim event. Remember, if your transactions reverts, then no event will be emitted. So in this case, it's safe to emit inside the for loop to avoid looping twice. If we reach the end of the loop, then it means everything is fine and we can mint the tokens for the user. The next function is buy premium token, which allows users to exchange the basic tokens for the premium ones. The principle is the same as before. We check conditions, we update the state, burning the basic token in this case. Then we do the interactions, minting the premium tokens. An external function to burn tokens is needed since we want these tokens to disappear right after use. This means that the mutated token contract will have to be allowed to burn mutation tokens whenever a mutation occurs. That's why the burn function will revert if the sender is not the mutated token contract. The next function is not meant to be used on-chain, but it's really important in order to get data from the dApp in an efficient way. Since this function has to loop through all of the Genesis tokens, it may consume a lot of gas to do it, even if it's just reading the blockchain. In order to avoid reaching the gas limits, I also implemented pagination, so we can split a call into maybe 4 or 5, depending on the collection size. It returns an array containing one claim status object for each Genesis token owned by the given address, plus a Boolean value that tells you if there are still tokens to fetch with further calls or if you already have all of them. The parameters are the owner wallet address, the start token ID for pagination, the end token ID for pagination, and remember these two IDs are from the Genesis token collection, and then the start balance must be set to 0 at the first call. Then you have to pass the number of tokens you received from previous calls. This allows the function to early return when there are no more tokens owned by the given address. The body of this function is not extremely complex. We are setting some initial values, then we loop through all of the Genesis tokens in order to filter them by the owner and collect their claim status values. But there's an instruction that I want to point out, and it is the mstore call inside of the assembly code block. Since we don't know the amount of tokens owned by the wallet address in the given range, we have to initialize our result array to the maximum expected size. This means that if we don't fill up all the slots, then all the empty values will still be there, but in an invalid state. That instruction truncates the array to the correct size before we return it. I learned about this trick from the team behind ERC 721A because they are doing the same thing in their codebase. The URI function simply builds the token URI using the prefix, the token ID, and the suffix. The code for this type of string concatenation can be found in a lot of contracts. The next 4 functions are simple setters. They allow us to update some values in the contract state. Just keep in mind that the only owner modifier is used in order to prevent the execution from unauthorized wallets. The last function is used to make the EIP 165 calls return true for our custom interface, as well as it does for all the other ones. I will get more into detail about this in a dedicated video about interfaces. With these files covered, now you know what this contract does and how it works. And that's all for this video. In the next episode, we're gonna take a look at the mutated token. That contract will take the original NFT, the mutation token, and create the final mutated NFT. As always, if you have any questions or anything you would like to see in the next videos, please let me know in the comments. Thank you for watching, and bye!